So, hi everyone, and welcome to my talk combining both analytics and real-time workloads all together. As Doug said, I am Felipe, and I work as a solution architect at ScyllaDB, and I am also one of the authors of Database Performance at Scale, an open access, freely available publication, which I have used in order to come up with the contents for this presentation. The title of today's talk is You Put OLTP in My OLAP, which is a bit misleading, to be quite honest with you, but that's something I have only realized a few days ago when working on my slide deck. The actual title rather should have been You Put My OLAP in My OLTP. But is there a difference? OLAP in my OLTP or OLTP in my OLAP? Well, let's see. As you know, there are basically two fundamental approaches involving how databases store data on disk. We have row-oriented databases, often said to be best for real-time workloads, and row-oriented databases store all data pertaining to a single row on disk. On the other side of the spectrum, we have column-oriented databases, often said to be best for running analytics, given the fact that it stores data in a vertical way compared to the horizontal partitioning of rows, as in row-based databases. And it turns out that this single designed decision effectively makes it much easier and efficient from the database perspective for one to run aggregations, perform calculations, and answer retrieving sites, such as, for example, top K kind of metrics. So, literature tells us that if you want to run OLTP workloads, it's best for you to stick with a row-oriented database and use a columnar one instead for your analytics workloads. Contrary to popular belief, there are a variety of reasons why people would actually want to run analytics on top of their real-time databases, such as when organizations don't want to deal with data duplication and the complexity and overhead associated with maintaining two separated data stores. Other factors could potentially involve the need to extract insights in less frequent intervals, for example. All that said, I do have to tell you that ScyllaDB is a wide column database. It is primarily meant for high throughput and low latency real-time workloads. Therefore, it doesn't necessarily classify into the columnar or analytics-specific realm of databases. However, if you are struggling with running your analytics workloads alongside your real-time ones, then you may want to consider checking on us, or at least check out how we are tackling this problem, which is the subject of today's presentation. But what is the problem which we are trying to address here? And it is very simple, actually. So this slide demonstrates the behavior of what happens when you try to run two workloads alongside one another. The green line represents a real-time workload, whereas the yellow one represents an analytics kind of job running. While the OLTP workload is running alone, latencies are great. But as soon as the OLAP workload starts, the real-time latencies dramatically rise to unacceptable levels, as we can see in the metric snapshot I have taken. Analyzing the problem further and looking at the throughput, we can very clearly realize the reason why latencies climbed. It turns out that the analytics process is consuming a much higher throughput than the OLTP one. And we can even see that the real-time throughput drops considerably, which is a clear sign that the database got overloaded. Unsurprisingly, as soon as the OLAP job finishes, the real-time throughput raises back to its normal levels and is then able to process its backlog of queued requests. Therefore, given all of these symptoms, we ended up actually introducing contention to the database. That is, we have two totally different workloads competing for resources in an uncoordinated way. And the database is naively trying to process all requests as they come in. But why does contention happen in the first place? Well, it happens when you submit too many requests against your database in a way that it is simply unable to keep up. Most of the time, it means your database lacks either CPU or I/O capacity in order to fulfill your requests. As a result, requests queue up and latency climbs. Beyond the database architectural definition, it is also important for us to understand the primary characteristics and the differences between the two types of workloads we are trying to execute and run concurrently. That is, while OLTP applications will often process many smaller transactions and are very latency sensitive, OLAP ones generally run fewer transactions, but those fewer transactions require the database to scan and process through large amount of data in order for them to perform their aggregations. Still, we now just understand the problem, but how do we actually solve it? Well, one often employed strategy is to simply physically isolate these resources. For example, in an Apache Cassandra deployment, you would simply add a new data center and separate your real-time processing from your analytics one. That's definitely a possible alternative, which avoids you having to string data and to a different and work with a different database. But at the same time, it considerably elevates your costs. So at the bottom of this slide, I have added two references should you be interested in learning more. The first one is from InstaCluster, a managed services provider, with a benchmark showing their results after isolating their deployments as pictured here. And at the bottom, I added a talk from Gangan, which they gave in Cassandra Summit 2015, where they basically employed the same strategy discussed here. And why am I adding those references? So we can understand that there are definitely use cases and organizations running analytics jobs on top of real-time databases. But the question we should actually be asking is, are there any other alternatives to resolve the problem other than this approach? And yes, there are. So another strategy some organizations employ is to guarantee that they don't run their analytics during their peak periods. That is, they simply run through their analytics pipelines during off-peak hours in order to mitigate the impact on latencies, as we have seen a few slides back. Take a food delivery company, for example. Answering the question of how much has a given specific merchant sold, which in the past week is really simple for OLTP. However, offering discounts to the top 10 restaurants which sold the most is a much more complicated insight to extract. And in a wide column database like ScyllaDB, answering those kinds of queries will inevitably require a full table scan. Therefore, it would make sense for such a delivery company to run those analytics jobs past midnight until around 10 a.m., as their peak traffic would likely start after we approach lunchtime, right? This is actually a doable strategy, but it still doesn't solve the problem. For example, what if your data set doubles or triples over time? This is natural characteristics of analytics. Your pipeline may overrun your window. Not to mention the fact that your business is still running. People still order food at 2 a.m. Even I ordered a hamburger the other day. So, in the end, you still want to tune your analytics job in such a way that it doesn't simply kill your database while your business is running. Um, and then we finally get to ScyllaDB's approach to solving the problem. A feature we named as workload prioritization. So the concept behind it being that you can simply define separate workloads and assign different shares of resources to them. For example, this slide demonstrates the definition of two service levels where the main one has 600 shares and the secondary one has 200 shares. Internally, and as we can see on the right side of the screen, ScyllaDB has a scheduler, which will process 3 times more tasks of the main workload as opposed to the secondary one. And we can visually see how it works. And we can see that whenever the system is under contention, the system prioritizes its resources allocation accordingly. But one of the questions you may have is, okay, so why does this feature only kicks in during contention? Well, it's actually a simple answer, because if there is no contention, then it means that there is no bottleneck. So there is effectively nothing for the database to prioritize. Our requests which come in are served immediately. All right. So workload prioritization, or even the concept of resource isolation, are not necessarily a new concept in ScyllaDB. We introduced workload prioritization as an enterprise-only feature back in 2019. And under the hood, it relies on seastar scheduling groups. Let me break it down for you. Seastar is a C++ framework for data-intensive applications, which ScyllaDB and other technologies such as Redpanda are built on top of. Scheduling groups are effectively the way seastar allows background operations to have very little impact over foreground activities. For example, in ScyllaDB and database-specific terms, there are several different scheduling groups. We have a distinct group for compactions, streaming, main tables, and so on. If you are familiar with Apache Cassandra, then you might have eventually found yourself in a situation or heard about some story where compactions could drag down your entire workload performance, right? Well, in ScyllaDB, all compaction resources are scheduled by seastar, and according to its shares of resources, the database will allocate a respective share to the background activity, compaction in this case, and therefore it will ensure that the primary user-facing workload won't suffer due to those background activities. Another benefit of scheduling groups is the fact that the database can auto-tune itself. If the workload is under off-peak hours, for example, then the system will automatically have more spare computing and I/O cycles to spend, and thus the database will simply speed up its background activities. All right? So, as I have said, workload prioritization, or simply this notion of isolating resources, It's not necessarily a new aspect in ScyllaDB. Ever since we introduced the enterprise feature, we have learned a lot, up to a point where, even though it greatly addresses the problem, we've found out that just that is not enough. When we mix real-time and analytics workloads all together, there are other important characteristics which we need to account for, which clearly distinguish one workload from the other. For example, when communicating with your database, you always want your server timeouts to be lower than your client timeouts. If you don't ensure that, then a premature client timeout may introduce a phenomenon known as retry storms, which can be very detrimental to performance. So if you have never heard about retry storms, I highly recommend you to open Google and Google it, retry storms. It's a very interesting phenomenon. All right. But the question we should be asking here is, given the notion of timeout, what is the right timeout to configure on the server side? Well, if it is an OLTP workload, it cannot be too high. Otherwise, your end user's bounce rate may increase, or they may simply keep retrying the requests in the hopes that it will eventually succeed. For example, think about an user clicking a button like nonstop and sending requests, spamming your database with requests. So what happens is that as a result of these retries, your database will end up wasting resources. On the other hand, for an analytics workload, the timeout cannot be too low, as we expect queries to take longer anyway. If the timeout is too low, the batch has a high chance of failing. And then there is the problem we have seen at the beginning of this presentation, where where the throughput of an analytics job may heavily increase and elevate the latency of real-time workloads due to contention. All right. Another characteristic that differentiates both workloads relates to how the database should respond in a scenario of being overloaded. And the thing is, we can't really throttle down an OLTP workload. It is real time after all, which means that even if we throttled our requests from user A, another user B would just keep sending requests against the database anyway. That said, real-time workloads often are characterized by having unbound concurrency, which is not necessarily a bad thing per se when your database can cope up with the pace of incoming requests. Analytics workloads live on the other side of the spectrum. We can just throttle them down, which, yes, will delay their processing, but at the same time, will guarantee that our OLTP throughput and latencies remain under control. By throttling the analytics workloads, the flow of requests is kept at a certain pace, and the application knows it needs to slow down, thus progressing with a bounded concurrency. So, all these differences and a few more led us to introduce workload characterization, which is a way for you to further hinge the database over the characteristics of each set of workload and control its behavior. As a result, we may now prioritize real-time workloads, dedicating most available resources to them, while still running analytics and still allow them to be performant. So this is the open source analytics conference. So of course, workload characterization is available in ScyllaDB open source, and you are able to create separate service levels and specify distinct timeout settings and define the type of workloads which will be running on top of each one. The concept of shares That is, the notion of prioritizing access to CPU and I/O resources within the system is still a ScyllaDB enterprise exclusive feature. All right. So the question at this point, you're probably wondering, all right, so did we resolve the problem? Well, the answer actually is not really, because while the features I just mentioned primarily deal with CPU and disk I/O, there is still one critical component left on ensuring that your database is actually capable of keeping your real-time workload latencies under control, which is memory. So, as we know, analytics workloads often need to scan and read through vast amounts of data. And this data will basically be populated to the database's cache. As a result of all of your analytics job reads, what happens is that important items potentially required by your real-time workload will end up being evicted. And its latencies will inevitably climb as now your real-time workloads will require reading more often from disk. So the slide on the screen demonstrates the ScyllaDB monitoring stack, specifically under its cache part. So ScyllaDB has its own cache implementation, which is a read-through kind of cache. So anyway, anytime you read some data and this read has to go to disk, the contents of that read will be populated in the cache. And if you have heavy analytics and workload and the real-time workloads running concurrently, what will typically happen is that you are going to see several row evictions and partition evictions happening frequently. And inevitably, due to that, important items in your cache will no longer be present, and your real-time workload latencies will suffer. So, to avoid this effect I just described, the effect of cache pollution, ScyllaDB also comes with a feature which we call bypass cache. So bypass cache allows you to read data from the database without it having to populate its cache from the contents it reads. For example, if you were to read a particular piece of data unlikely to be read again in the future, that would be a great candidate for bypass cache. If your analytics workload often relies on full table scans, you will probably want to include that clause in your queries as well. So I have spoken a lot, and at this point, you are probably wondering, how does ScyllaDB handle real-time and analytics workloads running alongside each other? Well, pretty nicely. These are the results for both throughput and latency. What we can see that, well, basically the kids stopped fighting and real-time latencies are now under control and both workloads can live happily along with each other. It's important here for us to still notice that yes, the real-time workload latencies climb up a little bit, but not dramatically as it was before. Similarly, on the throughput side, we can see its throughput declines slightly, and but again, not as much as it was before. And the reason why this happens is very simple. There is still contention. The database is now just prioritizing one workload rather than the other.